Okay. All right. Again, as I said, just plan on tomorrow. Just taking a day off. My body is just telling me bad things that there, and that's just one of the issues of being old. I think I shouldn't say. I don't think that's a. I there's something called stroke fatigue where your brain just wants to shut down. And this morning I felt it coming a little bit. It's getting worse, so I'm thinking that there. But who knows? I may go home after this class and sleep for 6 hours. I'll feel great. Not there, but I'll go ahead and just plan on taking a day. And I think I said something about that earlier in the semester that my body has to do that every now and then. And they've got me scheduled for 4 classes in a row, or 4 days in a row coming. Even though it's only for an hour or two class, it's still, by the time I drive here and prepare, it's still a 3 hour that there. Yeah, I just need to do that. Okay, let's get back to what we're here for. Is the objectives of this chapter is to start writing C code. This is the 3rd week of the class, and we've had one holiday and that there. So we've had what, 3 classes so far. So there. Last time, as I recall, we went ahead and we did write a simple Hello World program, and you're able to use the compiler. So if I leave you with a small C program from the textbook, you should be able to do it sometime between now and next Tuesday and look at that there. But we're going to cover, and this is actually a long chapter, but we'll get through some of it today. And I know my brain is there because my speech is starting to get tangled. That there. So, I'm not complaining, but one of the areas affected from my stroke was my speech center. If you've ever been around serious stroke patients, not people with the baby stroke like I had, you'll notice they have really bad slurred speech, and that they're right after that. My wife said mine was bad, but when I get tired, I notice it start that. So if my speech slurs today, I apologize ahead of time. So, okay, we're going to write some simple C programs. We're going to learn how to do input and output right there. So what we're going to learn 2 commands. Our input command, and we'll see it in more detail, is scanf, which is the most cryptic version of input commands that I've seen. BASIC uses the word input. Pascal uses input. Python uses an input function. C uses scanf right there, and I'll explain where that comes from. And print uses printf, that's there. And we'll look at that. Then we're going to look at some fundamental data types, such as characters, strings, integers, and that was introduced a little bit in the first chapter, right there. We'll talk a little bit about memory concepts, but not in great detail. And then we're going to learn how to do some arithmetic, add, subtract, multiply, and divide. That there. And notice that I use the word arithmetic, not math. Math is more detailed, right there. I am very good at math. I'm not very good at arithmetic. There are, and I have to explain to a lot of people that those are 2 different skill sets. Being able to find the integral of a function or the derivative of a function or determine the Z transform from a Laplace transfer function is different than to be able to add up a column of numbers. The good thing is that I've got spreadsheets today and computers to do the arithmetic for me. That there. I would make a terrible accountant. I'm dyslexic to a point. That there. So I transpose numbers. In a prior lifetime, for a very short period of time, I worked for a police department. Actually, it was the Indiana State Police as a dispatcher, which meant that police cars back. This was back in the this is from the 80s or the late 70s. You know, they were still using radios, and we had the old computer consoles in there, and they would read license plate numbers to me, and I'd have to write them down and put them in the computer. And I could transpose digits like you couldn't believe. Not a good job for a police dispatcher out there. I was actually supposed to be the radio technician, but for whatever reason, radio technician also had to do dispatching. And I could repair the radios, but I couldn't operate the radio out there. So, but regardless, arithmetic, we'll learn that we have to write our arithmetic functions a certain way in order to get the right result, right there. And then finally, we're going to look at some decision making. That's there. This is almost a mini course in C in just this chapter, right there. So again, this just is kind of the subject settings out there. We won't get into much on the secure C programming side out there. That's actually a topic beyond this course. Okay, this is one of these slides that I'm not going to agree with, but I'm going to go ahead and read it and explain what it says. C facilitates a structured, disciplined approach to computer program design. C is a high-level language, but it also allows us to do a lot of things that will get us into trouble. C allows us access to low-level hardware. It allows us to bypass good programming techniques. That's there. So this slide says that it facilitates a structured and disciplined approach. It facilitates, but doesn't require. There are languages that almost force you into being a good programmer. But one of those languages is one called Pascal. And Pascal was one of the early languages I learned. It's not used much anymore. Most experienced programmers hate the language. And the reason they hate the language is that it doesn't let you do anything stupid. That's there. But C allows us to do the program in a smart way, but it also allows us to do stupid. That's there. In other words, take shortcuts in order to make our code run faster, to save typing, and to, just get the job done quickly. But in the meantime, when we run our code, it could end up doing some really nasty things in terms of the fact that, yeah, we got the code written down very quickly, it looks good, it runs good, but then maybe sometime down the road, a certain set of data comes into it, and it just blows up in our face, right there. And that happens in almost all computer-based systems. None of you are old enough to remember back with Windows 7 and previous version of Windows, they used to have the blue screen of death. Has anybody ever heard that term, the blue screen of death? BSOD. And you're sitting there running Windows, and all of a sudden you get this big blue screen with no graphics on it and some text in the left-hand corner saying something bad happened. Usually some kind of error message that you have no idea what it means. And that's basically means that the hardware, something in the code failed, right there. And it could be the hardware too. I mean, I've seen many blue screens of death because of a defective memory module, a cable that's loose between the hard drive and the computer. But the blue screen of death just simply means whatever you were working on is gone, and you can reboot the computer, and 95% of the time it comes on. I've had the blue screen of death where the computer never came back on, and I'm replacing motherboards and digging into repairing hardware issues. But regardless, that's there. So C allows us to write code that facilitates crashes if we're not careful. So that's there. So this chapter will introduce some examples on how to write C. I'm not going to write C in this particular course in ways that I consider harmful to your code, but you can see if you can take that there's shortcuts you can take. That's it. So, and I don't know if this book's got it in this. I think it's in this book. If you read the chapter, he introduces something called the Shirley Temple theory. But unfortunately, he's old like I am. I think Paul Dechtel, the father, I think that's Father Paul. I can't remember which one's that there. But he's old enough to remember a movie series from back in the 1930s and 40s with a woman with a little girl that was like this tall called named Shirley Temple, and she was just the cutest little girl during the Depression. I mean, she was that there. So the Shirley Temple theory says don't be too cute that there. So you want to make sure your code is readable that there. So now chapter 3 and chapter 4 we get into more of the structured programming, how we write structured programming. And we're only going to cover the first 6, 7 chapters in this book anyway. All right. So you've already written your first line of code. We'll look at it here. I'm just going to go through the slides, and then I'm going to kind of leave it to you tomorrow or whenever between that there to just try some of these examples from that there, and I'll give you a short little program. This is the basic format here, and this is where I wish my pen would work, and it doesn't. Hold on, it works today. That there. Some rooms it doesn't work in, so I guess that's the other advantage. Any line that begins with these green, or anytime you see these little 2 green bars that there, that basically means that everything after that is a comment. It's ignored by the computer out there. And normally, when you write code, you will want to comment them in various places. The reason for the comments are simple. It helps you later in life or somebody else to know what the program does what in the program, and when something breaks or changes, you know where to make changes. Code is dynamic, it changes. That there. Yeah, that there. So these are just little notes that you want to keep. There's comments that there. So this simply says this is figure 1, my first program in C. This is normally, from a student standpoint, what you would normally put in the comments should be the assignment, you know, what your assignment is, what, you know, this is assignment such and such from the book, you know, obviously your name should be part of that. You know, any lab partners that you work with, if this was done as part of a team, right there. So that's usually the first part of this. If it's an industrial project, sometimes it will contain the, you know, the project ID. You know, I worked on a number of projects for various operations, and we had project numbers that there, or contract numbers that there. And that was true even for both the defense and the commercial world. I worked for a company that did a lot of contract work, the Indiana Microelectronics Center, where I did quite a bit of C programming for them. I was actually their only microprocessor person that there. And then I also did a lot of VHDL for hardware design. VHDL is a different language. And I really didn't talk about that. I think I'm going to take a second to talk about that there. And this is not in the slides, but when we look at languages that there, and I'm going to just call this programming languages, and what the heck happened there? I don't know. Programming languages. 90% of the people look at the software side right there. And that's where we got ASM, we mentioned that, C, Pascal, Python, and a whole bunch of languages that you think about. There's also a group of languages that are on the hardware side, and I got to be careful not to put my hand on the screen. That's what's that there. Hardware side. And hardware, and I'm going to call it description language right there, DSCLG. Description languages right there. These are languages that actually describe what we want our hardware to do. And these languages are a little bit more difficult to use, and they are a little bit different in the respect that programming languages generate a series of instructions line by line that we want the computer to follow. That's what a computer language, like the recipe of the cake. Do this, do this, do this, do that, right there. How do I replace the spark plugs in my car? Lift the hood. Usually you would do that before that. Latch the hood where it doesn't fall on your head. That there, identify, a spark plug by following the cable and pull off the wire. Put the socket wrench there. Loosen the spark plug in. Carefully put the new spark plug after adjust the gap on the new spark plug to the correct gap size. And guys might understand this better than girls. I'm sorry, gals, but there's something called the gap size. Is how far the plug that they're in. If it's too wide, then the spark won't jump far enough in order to light the fuel in the igniter. If it's too close, then there's not enough spark in order. But it's got to be a certain optimal distance. So you adjust there. Thread the new spark plug into the engine block or engine head carefully. Don't do like I did and put it in the socket and strip the threads out and have to remove the head and retap the socket hole. I did that one time 40 years ago. One of my first times working with an aluminum block engine. I just completely stripped out the threads and couldn't get the spark plug back in. And I had to drive it on 3 cylinders to the Datsun dealer that was before it was Nissan and get the head removed. And that was an expensive spark plug repair. But you follow these directions. Hardware description is where you describe what your new IC is, what your new digital chip is, or your new analog chip. So we're describing a piece of hardware with a programming language. And there's a number of those out there. Verilog is one, and VHDL is the other. Those are the most popular two. There are some others. Verilog is more popular in Asia. That's there. And it's actually probably the easier of the two. VHDL is a little bit more popular in Europe or Western Europe in the United States. And there's a reason for that, and it's fairly simple. VHDL was developed and designed and paid for by the United States Department of Defense. And they require that anything done for the Department of Defense is done in VHDL. And by extension, anything done in military hardware for NATO countries must be done in VHDL. So as a result, Western countries tend to use VHDL more. The non-NATO bloc, and NATO is North American treaty organization, but it's a defense organization in Western Europe and the United States to fight the Russians, which that's neither here nor there, but it's a military treaty organization. There's also one for Southeast Asia, but it's not nearly as powerful. That's there. So, but regardless, VHDL is a hardware description language. And things like microprocessors are designed in VHDL. Memory chips are designed in VHDL. Camera image processing chips are designed in VHDL or Verilog. A custom IC, not a microcontroller, but a custom digital IC that will control a microwave oven or the ignition timing system of a car would be done in Verilog or VHDL. So we're designing hardware. At the end of the day, when we design something with a hardware language, it actually becomes a piece of silicon. Now, some silicons are field programmable. They kind of act a little bit like microprocessors. You can erase them, put in new designs. Some of them are done in what they call mass, and they're produced with the hardware design already completely built into them. So these are things at there. So this is two different areas of programming. They look similar, they're different. One of the key things that's different with the hardware design programming languages is that you can have parallel paths. You can have three things happening at the same time because it's three different pieces of hardware on the same chip. I can have signals that are processed simultaneously up there. I can have custom counters. I can have custom encoders. That there. As a general rule, I've worked with both. I've done both. That's there. I loved working in VHDL. I haven't done a lot of real work in Verilog. And when I say real work, I've taught courses in Verilog. I've done some projects from the academic world. I have never did anything in Verilog where somebody gave me money at the end of the day for doing it. So that's what I call real work. If I'm doing a contract job and someone's going to pay me for doing the work, then I call that real work because there's real money changes hands. If I do something sitting at my desk at home, and I plug it into a FPGA board just to see if it works, and it works great, all right, that's going to be my next lab in my class. That's not real work. That's just academic work. So I've done quite a bit of work in VHDL. I worked for Raytheon, where we did, sonobuoys, work for the subs. I mentioned that project. I've done some work for General Electric where they did engine controls up there, and a lot of that work was done up there. The major difference between these two things, and this is a top-level engineering decision done probably above your pay grade when you first graduate, but in 5-10 years you may be at this pay grade, is whenever a new project comes along, a new product you're going to design, you have to decide whether or not you're going to do it with a microprocessor or a microcontroller, or if you're going to do it with dedicated hardware. And there's a lot of decisions that are part of that. Typically dedicated hardware is faster because the hardware is optimized for exactly what you're wanting to do. Typically the dedicated hardware is smaller because you only have what you need to do that particular job in the hardware. Normally the development cost for dedicated hardware is much higher because you're going to custom silicon. That's there. You're actually having to design silicon chips either at the gate array level where you're generating mass and you have to make factories where you see the little silicon wafers there. You're actually starting at that level. Mistakes are extremely expensive at the hardware design level. You make a mistake and you spent 100,000 ringgits designing a chip and it doesn't work. You're going to spend another $100,000 to do the next round. So typically you do field programmable stuff and one-time programmable stuff before you go to the custom, which is bigger and they're more expensive, but they test the design before. But sometimes they work in the prototypes, and then when you get the real chips back, they don't work. I actually worked for a company that I wasn't the project engineer. I did some coding, but my coding was not a problem. My coding was done right. But we had the project engineer on this particular one was not a degreed electronic or electrical engineer. He was kind of a trained himself, seat of his pants, and he did some shortcuts doing the custom, design, and there's something called synchronous versus asynchronous type designs, and there's some advantages. He did some stupid stuff. It worked on the slower prototypes in the lab. It worked perfectly. We spent the 15, 20,000 USD to have the first set of chips made. We installed them in prototypes at one of the customer sites. And 3 days later, went and had to hire a locksmith to remove doors, to remove them all. It was for like one of these little key locks for a door, but it was for hotels where you swap the key to get into your hotel room. It was one of the early designs from like maybe 30 years ago. We were working on that there. And every one of them failed after about 4 days. There was a little glitch in the hardware design, and they all failed. Unfortunately, the company that we were doing this work for ended up not being able to afford the second iteration and sold the company to another company. So, I mean, this was a very expensive mistake. I mean, we're talking millions of dollars that was lost. Not only in the fact of the iterations of the chip, but we're talking probably 6 or 8 months of engineering time to come up to this failure, and the contractual obligations for the company Again, my job was safe because I wasn't the one who botched it, but the lead engineer in the company who did this was looking for other employment shortly after that. So I mean, these are things at the design level. Software tends to be slower in comparison to dedicated hardware. It tends to be much easier to fix when there's a mistake. You can always do a firmware patch. You can always do an update. We mentioned, your cell phones. How many times do you get updates? Bug repairs on Windows, right there. Software is a lot easier to fix when there's something not done. You produce a whole bunch of airbags and sell them for automobiles, and there's a glitch in the hardware, the custom chip for the airbag, and they start failing and people start dying in car accidents because of them. Your company is going to take a serious hit, which has just recently happened, right? You've heard of I can't remember the name of the company. Talca, it's a Japanese company that makes airbag controllers for many, many car manufacturers. They've been involved in many, many lawsuits, and those are all custom design ICs. The other thing about the hardware versus the software, and then I'll get back to the discussion, is hardware is often much, much cheaper per unit once you cross a threshold of how many you're going to make. So if you're Apple and you're making how many millions of iPhones, and it costs you 1 billion ringgits to develop a new microcontroller, say the new A10 chip. I think the A10 is what they're using in the new version, or A9. I can't keep track of the Apple iPhone microcontroller chip, but you may spend 1 billion ringgits developing that, but you're going to sell 100 million of them, right? So you're only talking 10 ringgits per phone in the R&D costs, right there. So you will spend a lot of money. If you're General Motors, you know, the big automobile manufacturer in the US, and you're making millions and millions of cars that are all going to use the same engine controller IC, then you're going to do a custom chip. That's there. But if you're going to be making, for example, a lock you sell for the front door of houses, you know, a digital lock or one that's controlled by a cell phone, and you know, you're a small business company and you're hoping to sell 500 of them your first year or 5,000 of them your first year, you can't afford to do a custom IC. That's there. So and that's why I'm saying these decisions are going to be made above your pay grade when you first start working, because it's not just, you know, which one's fast or which one's that there. There's economic decisions, there's risk factors taken that there. And then there's also some cases where the custom IC is the only solution. If I'm trying to build an image processor to put in a satellite 50 miles in space, and this thing has got to be super fast, super small, super low power, because it's going to have to operate on solar power for the next 20 years, it's probably going to be custom. It's probably not going to be software, because I can't afford to have a microcontroller, additional memory. I can't afford the power consumption. I can't afford the space. That's there. If I'm going to be dropping something in the ocean, and it's going to have to operate on a battery, and it's going to have to do a lot of processing, and the thing's going to be small enough, it's probably going to be a custom IC, because, again, it's not the best solution from an economic standpoint, because something like a sonobuoy, and I think I mentioned what a sonobuoy was before, is a one-time use device. You use it one time and it self-destructs. That's there. So you don't want to put a lot of money in each one of them, but you also have to realize that there. And then security, you know, this is a thing that a lot of money was developed to develop the software to listen to submarines, and you don't want, you know, your enemies to pick up one of these things off the bottom of the ocean and reverse engineer the thing. It's very hard to reverse engineer an IC that's manufactured right there. So that's my little sidetrack. It's not really part of this course, but it's just part of my experience that I've worked on both sides. Now, this is in the embedded world. This is not in the desktop world. That's there. The only place this is in the desktop world is in the microcontrollers and the microprocessors and those things. And with cell phones, there's a lot of stuff in both areas. The early cell phones were all embedded or custom hardware. Now most of them are using, they're using microcontrollers, microprocessors with operating systems. So that's changed. All right. Getting back to our discussion right here with C, right there. And this is where we're supposed to be at, and I completely muddied it. We have our comments right there. There are comments that's there. So our comments will often have the project number, what this particular program does. Many projects have multiple files to them. Nothing we're going to do in this course, but you can have multiple files for a particular project. That's there. Every project has to have in C one function called main. That there. There must be a function called main and only one function called main. Because when the compiler and the linker locator takes your code and makes the executable version of your code to run, the operating system or the embedded microcontroller needs to know where to start right there. So C is a function-driven language. Everything in C is usually contained in a function. All executable code. Now, what do I want to say? Some variable declarations might be external to function calls, and the includes are usually external to function calls. But anything that's executable is always going to be inside of a function. And main happens to be the first function call. And when main ends, then control is returned back to the operating system. If you're in the embedded world, sometimes you write programs that you want to never end. If I write a program to control a gasoline pump, for example, a petrol pump, I use the American term gasoline, but you know what I mean by, you've seen enough American movies, you know, people stop at the gas station, not the petrol station in the U.S. We call it gasoline versus petrol. But you've got that pump that you walk up to it and you scan your debit card or you go in and you pay for your fuel and they authorize the pump. You take the pump off, you fill it up with fuel, and then once you reach the maximum level or the sensor senses your tank is full, it shuts the pump off. It puts pumping petrol. You put the hose back, and then it prints out your receipt and resets back ready for the next customer. You don't want that program to end. You want it to keep recycling back, process a customer, get ready for the next customer. Now, there may be a sleep mode where it's powered down at night if you have some petrol stations that are only open during the day. I don't think you don't have any of those in Malaysia, do you? In the States, we used to have a lot of those that would shut down at 8 o'clock at night or not that there. We used to have them closed at 5 o'clock in the evening. I mean, they worked on cars and pumped a little gas on the side type thing, the full service station. And about 5 or 6 in the evening, the owner and his mechanic went home for the day, and the station shut down. But there are not many of those ones. But those programs may have a shutdown mode right there. But for the most part, petrol pumps run 24/7. Now they may have a mode where they print out the daily receipts. They may have a mode where they, fill up, where it's fueling up the reservoir tanks, and it's kind of in a hold pattern. But typically, the program never shuts down. Right there. Same thing with your cell phone. You don't want the thing to go into shut-off mode very often. Right there. So when we're in the embedded world, quite often we have programs that will have I used to put in there a loop that would be until hell freezes over, and hell freezes over was a variable that was always set to false. Right there. I probably ought to have some kind of indicator. If it snows in Kuala Lumpur, hell freezes over is probably, the world's coming to an end. That's there. But regardless, we have this concept. Quite often you'll see while one right there, or while true. But every function has 3 things to the function right there. The first thing is, in this particular case, int is what main returns back when it's done running. Now, int doesn't have to return anything. I could leave that word int off there, or I can replace it with the word void right there. But int is the return value of the function right there. So now another example of a function might be, I'm going to call it float, and we'll explain this later. I don't know what that line there is. Float and sign right there. And I'm going to say that it's going to receive a double, for example, right there. Right there. And I'll talk about that. We'll talk about this later. But I can say y is equal to sine x right there. Sine is the name of a function. It actually happens to be contained in the math.h library in C. We'll talk about that there. We pass it a single variable right there, x. And then whatever the value of sine, there's going to be at the end of the function sine a word return and some value right there. And whatever it returns goes back into y right there. In this particular case, int isn't going to return anything because nothing calls main here other than the operating system. So right there. Then we have our function name, f name right there. In this particular right there. And then we have usually in parentheses a list of all the variables that are passed to main right there. If we don't have any variables passed to it, we can put either empty parentheses or the word void right there. But main is the name of a function right there. We'll be writing our own functions probably in the next chapter right there. Every block of code in C right there has a begin and end bracket right there. Braces right there. I guess those are called braces, not brackets. Brackets are the square ones. But begin and end that there. You'll see braces all over the place in C. They denote the beginning and the end of any block of code. And we use them lots and lots of places right there. So, and then we've got, in this particular case, one executable line. And we did one of those last week where we said printf and hello world right there. So printf is a print statement and it prints to the standard output device, which happens to be the monitor right there, the screen. And the F means that it's formatted. So we've got formatted out print statement. And because printf is also a function, that there, we're passing it one variable inside of a set, inside that parentheses. Now, printf happens to be a function that can contain multiple variables. And this is where C can get kind of confusing, is we don't have to limit ourselves to passing one variable, two variables, three variables right there. Main can accept a variable. So in other words, I can write a program that I'm going to call it square right there. That's the name of the code. And when I run it, I'm going to have to tell it the number that I want to square it. Now, that's a little awkward to do within our development system because we run our code from the environment, they call it the IDE, the integrated development environment. So we don't run it from the command line. Back in the old days of DOS and even in Linux on the command line, we would write functions such as delete abc.doc right there. So that's there. So we could pass it the file name we wanted to delete. And delete was a program written, at that time it was written in assembly language, that would go look in the current directory for a file with that name and would remove it from the drive. But we would pass to the program delete the name of the file we wanted to delete. Right. So there are main programs that will receive variables. We just won't see them in this class, and it's difficult to do it in this class using the interface that we're using. Because normally if you're going to be passing something to the main of a program, it's got to be contained in the command line where it's called. So, but printf in this particular case is receiving one variable, and it's actually not a variable; it's a constant. It's receiving a string, and the string is denoted by the opening and closing quotes, right there. And so we're passing the string "Welcome to C!" exclamation mark, and then we have the escape code /n, which means new line. Those are called escape codes. And then every line has to end, executable line has to end with a semicolon. That's our executable line separator up there. And our main ends with our closing breaks. And then we have the closing time. So this is the simplest C code. And you did one like that last week, right there. So, all right, now I talked completely about these slides, so I'm going to skip these slides. These just kind of say the same thing I said right there, instead of reading the slides right there. This I didn't cover, but this is another way of doing comments right there. Normally, you would use the / and the n* for multi-line comments. He says we prefer the / at the end of every line, right there. But if you wanted to say you're testing code, you want to block out a section of code that's causing some problems, I will use the /*. Did you don't block a code I want to comment out, and the * at the end of the code that I want to block out. That's there. It's not really used a lot, but a lot of companies used to use them quite a bit actually at one time, and I still see a lot of programmers do that. The /* and the // everything in between those two character sets is a comment. Fortunately, the IDE normally greens out with a comment, so you see what's commented out. But you could block out, 300 lines of code with 4 characters, right there. You don't have to put the / at the beginning of every line. And when I'm debugging and I've got some problems in code, or I want to skip a section of code while I'm testing something, I quite often will use the /* / right there. So the preprocessor, whenever you see this little pound sign, that you're telling the compiler to do this before it does anything else. It's called a preprocessor. And what this does is it's going to include a file in the code, so it's going to go out into the hard drive where C is installed. It's going to look for a file called stdio, standardIO.h. StandardIO.h is actually a series of header files, and we'll talk about what a header is later when we write our own functions right there. But it contains essentially what the definition of what printf and scanf is. Right there. As I said, everything in C is done in functions, and these functions are contained in a standard library someplace, and what these functions are expected to see and not see in terms of passing variables to them has to be defined someplace so the compiler knows as it's executing the code whether or not these functions are being called correctly. That's there. The second part of the compile process is the linking, where it actually goes through and ties the function calls to the actual functions. but the header is just simply a definition of what that there. C, by the way, I should point out, is a very, very tiny language. It doesn't have much in it. And most of the stuff is done with functions called out of the standard libraries. And one of the very powerful things to see, and that's not really part of this chapter, is that we can overwrite library calls. We can test things on the desktop. Then we can turn around and write our own version of printf. So we're working with it on the desktop, and then we change printf to write to an LCD display on a dashboard. Or the LCD display on our petrol pump. So we tested on our desktop. We're running printf, and it's showing up that there. And we don't have the petrol pump in front of us. But then later on, we interface the petrol pump to the keypad on the petrol pump and the card reader right there. So instead of using, scanf, we then rewrite scanf to read the keypad. We rewrite printf to write to the LCD display. But the preprocessor gets that stuff up there. It's just a lot of it there. Again, you can use white space and blanks. That's all taken care of. So again, I talked about this. And this just repeats the whole thing that one or more functions, one of which must be main. That there. Again, you must have one main in every program. Right there. Still got time here. Okay, so functions can receive, I mentioned that before, anything in the parentheses is information past that there. The word void means that we're not passing anything to main. Void means empty in this particular case. I know a lot of times in the US, people, when they cancel a check, they'll write void, saying it's no good anymore. Void in C programming actually means empty or nothing. That's it. We're not passing anything to it. So in this particular case, main is returning an int. Main, in most practical cases, is going to return a void right there. Good programming, again, every function should contain a comment. And again, that's a mandatory thing with some corporations. General Electric basically had a form that was actually included as a comment before every function we wrote, and every function was stripped out of our code and placed into a library of functions for every engineer in the company to look at and steal from if wanted, if so desired. Right there. Which made perfectly good sense. Why am I writing the code in order to control a particular function generator? Because a lot of our test equipment, we would have a function generator that we would want to generate a sine wave at 2.5 kilohertz at 1.5 volts peak to peak, right there. So, so I would write a function called gen_sine, and usually underscore in the model number of the function generator, and I would pass it, the frequency and the voltage. That's there. So, that's just my phone. That's there. But why would I have to, write that when there's already 16 of these function generators sitting on test stands out on the production floor already? That means that everybody who's wrote software for that particular function generator has had to use a similar function. Well, why don't every test stand use the same function right there? So, and it turns out we update the function generators, then we write a new version of that particular there, and then we just update all of our test programs with a new version. That's there. Instead of each person having to rewrite a new, that there. Same thing if you worked, I had a company, and that's why I mentioned petrol pumps. There was a company in Fort Wayne. I didn't work for them, but I've been to the company. I had graduates working there. Out there, Tokheim, which made gasoline pumps or petrol pumps. I don't know if they sold them in Asia or not, but they were quite popular in parts of the Midwest and U.S. But Tokheim was a large company that made petrol pumps out there, and they made them way back in the early 1900s, back when they were the mechanical wheels that go click, 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 click when you bought gas. That there, and of course they migrated to the electronic ones. Well, you know, they had probably 30 different models of petrol pumps, but they all use the same LCD display. Well, why would every person writing software for each petrol pump model, you know, the controller for it, rewrite the functions to talk to the LCD display? Same thing with desktop software. You know, that there. If you're writing mobile apps for cell phones and you need something that generates a calendar, do you use a standard library function for that? So that's there. So okay, this just goes through the whole thing that I talked about right there. Escape that there. Escape again slash that there. The escape code right there is right there. We will see lots of those different escape codes. There's a table later on that there. So when the new line appears in that there, and again, this slash n can be anywhere in the string. It doesn't have to be at the end of the string. It can be in the middle of the string. It can be at the beginning of the string. You can have 4 or 5 of these in the same there with the slash n right there. And I said that later on, slash n is new line. Tab means to tab it over if you want to put a table. Alert sounds a little beep on your phone or on the computer. Backslash is actually an escape code saying to print a backslash, because the character after the backslash denotes what type of escape code it is. So if you wanted to print a backslash, then you have to do a backslash. The same thing with the quote, because the quote denotes the end of a string. If you want to put a quote in a string, you have to do it as an escape code, character code right there. So again, this just kind of explains everything. Add a comment to the line containing the right brace, close every function. Basically, it says that at any time you put a right brace anywhere in your code, you should denote where what that right brace is closing. Because I can have a brace here and a brace here. This is for my main code right here. So I would put end main right there. I could have another brace here, and this could be for, so this would say end F statement right there. So I could have another set of braces right here, and I can say end for loop right there, which we haven't talked about if statements and for loops yet, but we've got 1, 2, 3 ending braces. One of the most common programming errors that drive young programmers crazy, I mean literally crazy, there is they forget to put a brace in a certain spot, or they put one too many in and the braces don't line up. You know, a lot of times when you troubleshoot programs and it's not working, you're getting errors, you print it out and you'll draw a line from this brace to this brace to this brace to make sure that they're all included in that there. You can have as many embedded blocks of code, and an opening and closing brace denotes a block of code. You can have as many of those as you want, but they can't overlap. Right there. One block of code must be contained entirely in the the current block of code. So in here, we've got 3 blocks of code that's there. So the braces have to line up. And when you tab under each other, you want to make sure that you try to get them where they line up to make it easy to read. That's there. Now, C, as I mentioned in the beginning of the semester, is probably one of the most cryptic languages for a first programming language. It's not an easy language. Python is easier, BASIC is easier, Pascal is easier. C is popular because you can do pretty much anything you want with C. You can talk to hardware, you can talk to the registers in the microprocessor, you can talk to, you can break the rules if you want to. You can do all kinds of things. So C is an extremely versatile language. It lets you do anything you want, including shoot yourself in the head. That's there. I mean, it literally lets you do stupid stuff. That's there. And sometimes you have to do really stupid stuff. That's there. In order to get the code to work properly. That's there. So, but if you're going to do really stupid stuff, be sure you comment really stupid stuff. I'm going to kind of end on this note. It's getting, I don't know what time it is here, but for the programming. Yeah, I'm about to my hour. That's usually where I'm at. But I remember writing a program one time, and hopefully I didn't tell the story before, and I remembered not to tell it again. But when I was at Magnavox, I was working on a system one time, and I had a function that refused to work. Refused to work. It would not give me the right answer. It would not work. And finally, I experimented with it. I went around and I found that I could make it work if I added max int to the result. I kept getting the wrong answer. I kept getting everything else. But what are these wrong answers got in common? And I found the common denominator, and I made it work. Made absolutely no sense why I had to do that. Absolutely no sense. It's like adding x plus y equals, z equals x plus y, and you're always off by 5,000. You're always off by 5,000. That's there. It's one of those really stupid things. So at the end of the day, you say, z is equal to x plus y, and then you throw another line as c equals c minus 5,000. And then you got the result of x plus y. That there. Made absolutely no sense. And I literally spent 3 8-hour days, I think, on this. And I still remember this 32 years later. I mean, that's how frustrating this particular event was. So, well, I got it to work. The code worked. Now, fortunately, I commented that with one of those comments like, don't ask me why and I put some choice words, Magnavox had mostly male programmers at that time, and if a young lady read my code, hopefully she was thick enough skin to put up with the kind language that I put in after 3 days of fighting with this, So I put that comment in there. The code worked great. No problems. The Navy was happy with the product. It went into production, and we used it for I I left Magnavox, decided that academia is where I wanted to go. I'd finished grad school, and so I decided to go that there. But I was still doing some part-time work at Magnavox, part-time. They were in the same town, and a lot of my students were graduates of the program that I went to work for. And I just remember probably 3 or 4 years after I'd left Magnavox. So you're talking a number of years after that. I get a phone call from a guy I knew, Brett. It's kind of like, oh, hi, Brett. He was a graduate. He graduated 2 or 3 years earlier from the program or something like that. And he goes, I go, what's up there? I haven't heard from you in a long time. How's things going? I guess you're over at Magnavox. You're up in, you're up in Garrett, where I used to be at. And then he comes back and he says, I inherited that code you wrote, 5, 6 years ago. And I go, yeah. What in the world is this thing in there, out there, in this comment that I put in there? I explained to him the story and everything. He says, well, is it okay if I comment out because it quit working? It's locked up out there. I said, try it, see what happens out there. So we talked about it. He commented out, and then he came back and said, well, it's working fine. I go, so I go, what's happening? You're recompiling the code, or they're changing the project? Because we had to recompile the code because the models changed, and some other parameters the Navy wants included that there. And next question came out of my mouth is, have you updated the did Hewlett Packard update the Pascal compiler that you're using? This was written in Pascal. I said, yeah, we changed Pascal compilers about 2 years ago. I said, well, yeah, well, I says, what we had was a bug in the compiler that there. So this is where comments really come into play, is that my original code that wasn't working had no problems with it. The problem was the compiler provided to us by Hewlett Packard, who we were using, at that particular time for our code development. Microsoft wasn't out yet with their compilers and that there. So we were doing work on a Hewlett Packard workstation in Unix that there, and and this was again 25 years ago that this happened. They didn't update compilers every year or two. I mean, and there had been a 2-year cycle, or 2 years prior. They bought a new compiler, updated the compiler. They fixed the original error in the compiler that forced me to have to write this stupid code to make it work. So then Brett just went ahead and removed that code. It was no longer necessary, and everything worked fine. But I'm kind of the stories aren't to talk about how old I am or anything about this, but to point out the need for comments and documenting code, because this particular program, as I recall, and this was old style Pascal code, we had some job control language built into it, and some other thing, 3 or 4 different languages, was probably about 400 pages in the entire project. And without that particular comment sticking out like a red flag, and this one stuck out with like a red flag because it had languages that was not politically correct because of my attitude at the time. And that was well before I became a Muslim, and I sure wasn't a very good Christian at that time, looking at the language in that particular comment. But because of that very strong language and the fact that that comment stuck out so blatant that something wasn't right here, that Brett zeroed into why this big 400-page program wasn't working and we weren't able to get sonobuoys out the door, that there. And of course, the Navy's screaming every hour that we're not producing sonobuoys because we're going through them like water. It was back here in the Russians. But the fact that that comment was so clear actually probably saved hundreds of thousands of dollars for the company because production didn't shut down because it was such a quick fix in order to do that there. Otherwise, I could see him spending months going through 400 pages of code trying to figure out what functions were malfunctioning and causing that there. And this was going into firmware in a system. So I'm going to kind of stop at that there. I'm actually over my normal hour and 10 hour a minute, but since we're taking a holiday tomorrow, this counts as a double class almost. That there. So